So welcome to our online class. Today we shall be discussing Gay-Lussac's law. So for Gay-Lussac, compared with Boyle's or Charles' law, um, the only variable involved here is going to be your pressure and temperature. So for Gay-Lussac, the volume or the space that your gas will occupy will remain constant. It will not change. So the volume is going to be your con the volume is going to be your constant. Okay. So how do you change the pressure and temperature? So one of the ways you do that is going to be, for example, let's just say you place fire or heat coming from the outside that will change the pressure of your setup. So again, for pressure, we're going to try to use atmosphere all of the time. And for your temperature, we are still going to use Kelvin, just like the first video. So our formula goes this way. P1 over T1 is equal to P2 over T2. One of the main problematic type of equations are equations that looks like this because there will be too much work. However, you can simplify this situation right away. So first, I'll try to simplify this formula for you. So to simplify this, first we multiply both sides by T1. Cancel, cancel. So you're left with P1 is equal to P2 times T1 over T2. And to make it much simpler, you just multiply both sides by T2, cancel the T2 on the other side, and you multiply the other side by T2. So your the final formula that you use to make it easier to solve would be P1 times T2 is equals to P2 times T1. This will be the formula that we are going to use for all of the 4 problems that we are going to encounter today. And again, if you want to pause on the video to try to solve first before looking at how I solve the problem, then you may do so. So let's start with the first problem. Okay? So at constant volume, remember the volume will be constant, a sample of an oxygen gas with a temperature of 27 degrees Celsius and pressure of 2 atmosphere is in a closed setup. What will be the pressure in atmosphere if the temperature is increased to 127? Again, a simple review of our problem solving. So to convert your Celsius to Kelvin, C divided by degrees Celsius, so the temperature, plus 273K is going to be your Kelvin temperature. So, for example, your temperature number 1, which is 27 degrees Celsius, divided by degrees Celsius plus 273K is going to be 300 Kelvin. And your T2 is going to be 127 degrees Celsius divided by degrees Celsius plus 273 Kelvin. So cancel Celsius, you'll end up with 400 Kelvin. Now, let's try to identify your given. So the pressure and temperature are the ones that we are going to look for today. So P2 and T2. So P1 is equal to 2 atmospheres, so no conversion needed. For your T1 is going to be 27 degrees Celsius or 300 Kelvin, and then 127 degrees Celsius, which is going to be your 400 Kelvin. Now we're going to solve for P2. Remember the formula that we did a while ago on the first slide. So P1 times T2 is equals to P2 times T1. So we're trying to look for your P2. All you have to do is divide both sides by T1. So divide both sides by T1. Cancel T1 on the right side. That would mean P2 is equals to P1, which is, your P1 is 2 atmospheres, multiplied by T2, which is going to be 400 Kelvin divided by 300 Kelvin. So cancel both of the Kelvin. So 2 times 400 divided by 300 is going to be 2 point, okay, divided by 300 is going to be 2.666 6666 and so on. That would mean your final pressure is going to be 2.67 atmosphere. So if you've noticed, there was an increase in temperature. Now what happens to your pressure? It also increased at the final pressure. So Gay-Lussac is pretty much the same with Charles' law. If the pressure increases, the temperature increases. If the pressure decreases, the temperature decreases as well. So the next problem. So you have here your temperature and your pressure. So pressure 1 and temperature 1, and then you'll have pressure 2 and temperature number 2. So pressure 1 is going to be 1,500 millimeters of mercury. Your temperature number 1 is going to be 100 Kelvin. Your pressure number 2 is going to be 1,000 millimeters of mercury. You are being asked what is the T2 of this problem. So first, we have to identify. We have to convert your pressure into atmospheres. So for example, P1. Okay, so P1 is equal to 1,500 millimeters of mercury. So we are going to convert it. Just look for your conversion table. 1 atmosphere is equals to 760 millimeters of mercury. So 1,500 divided by 760 is, okay, divided by 760 is going to be 1.97 atmosphere. Okay, cancel. So you have 1.97 atmosphere. That's your P1, 1.97 atmosphere. Now P2 on the other hand, so we'll use 1,000 millimeters of mercury times 1 atm divided by 760 millimeters of mercury. So 1,000 divided by 760. So your P2 is going to be 1.32 atmosphere. So what happens here is there is a drop in your pressure. That would mean there would also be a drop in your temperature. So to solve for T2, P1, okay, P1 times T2 is equals to P2 times T1. So T2, to solve for T2, you have to divide both sides by P1. Cancel P1, you'll end up with T2. T2 is equal to P2, so your P2 is going to be 1.32 atmosphere multiplied by your initial temperature, which is going to be 100, then divided by your initial pressure, which is going to be 1.97 atmosphere. So that will be 1.32 times 100 divided by 1.97. So your temperature is, your temperature, so cancel atmosphere, then you'll have Kelvin. So your temperature is going to be 67.005 or 60.001 Kelvin. This will be your final temperature, 67.01 Kelvin. So if you've noticed, there was a decrease in pressure. Now there would be a decrease in your temperature. So last two problems. Okay, so this one, what is the initial temperature of your sample? So you have here the initial pressure is going to be, okay, so you have here two pressures and two temperature. Okay, so for this problem, your given is not your initial pressure and temperature. So at constant volume, a sample of ammonia was changed to 3 atmosphere. So 3 atmosphere. And then your temperature is 452 K. So the other given was if the initial pressure was 5 atmosphere. So 5 atmosphere, what will be the initial temperature? So if you look at this problem, there was a decrease in your pressure. That would mean, okay, your T1 is going to be higher than your T2. So P1 times T2 is equal to P2 times T1. So to solve for T1, divide both sides by P2 and cancel P2. So T1 is equal to P1 times T2 divided by P2. So P1 is your 5 atmosphere multiplied by your T2, which is going to be 452 K divided by 3 atmosphere. So 5 times 452. Okay. So where was that? Okay. So 5 times 452 divided by 3 is going to be, okay, it's going to be cancelled the ATM, so it's going to be 753.333 and so on Kelvin. So there was a decrease because there was a decrease in your temperature from the initial to your final because there was a decrease in your pressure. So lastly, I have to discuss this two things. Three formulas. So if you look at them, so P1 times V1 is equals to P2 times V2, and then you have your Charles law, which is your V1 divided by T1 is equals to V2 times T2. If you've noticed, the pressure and the volume has their relationship. The volume and the temperature has their relationship. The pressure and the temperature has their own relationship. Which only means, to simplify, these three gas laws can be combined into one equation. You call this the combined gas law. So that means P1 times V1 divided by T1 is equals to P2 times V2 over T2. Anyways, that's all for today. Hope you learned something, and we shall be discussing the combined gas laws for our next video. That's all. Thank you and see you next meeting. By the way, I'll just give you this as a, okay, I'll just this since it's not working very well. Okay, so I'll just give you this as a homework to work with. So this, I want you to try to solve this. At constant volume, a sample of hydrogen gas was changed to 2.5 atmosphere and 115 Kelvin. If the initial temperature of the gas was 150 K, what is the initial pressure of the gas? So you were given the P2 and T2, and you have to solve for the P1 of this setup. That's all. See you next time, and bye.